Hello, my name is Franz Bieker and I'm welcome you here at the IT conference, and I'm proud to present i-TRIBOMAT. It's an European project and an intelligent open testbed for materials tribological characterization services. This is a co-talk with ANSYS Granta Great Britain and AC2T Research from Austria. Before starting the presentation, I want to introduce the presenting team. Donna from ANSYS Materials Business Unit in United Kingdom will talk about material informatics, material databases, and Ulrike, she will talk about the material simulation. And also I want to thank our colleagues Sarah, Sunil and Marine for supporting us to prepare this presentation. Many thanks. First of all, some key figures of our project. i-TRIBOMAT, it's an intelligent open testbed for materials tribological characterization service. It's an H2020 project with a funding of about 7 million euros and resources about 800 person-months. And please note, i-TRIBOMAT is not an ordinary research project. i-TRIBOMAT aims to build up a sustainable business. The motivation. Our motivation is a very industrial motivation. It's industrial driven. We want to reduce time to market and want to reduce development costs. The question is, can a material be applied in an industrial system? Is the tribological performance regarding functionality, reliability, efficiency proper for the new product? So we want to set up material characterization services to predict this product performance in an early stage. The implementation of i-TRIBOMAT is shown in this picture. It consists of 4 interacting units, starting with the shared infrastructure. 5 tribology centers are sharing their infrastructure, like tribometers or triboanalytics equipment, and they are connected via IoT technology to the IT platform. This enables us a standardized tribological testing. By storing the data in the IT platform, also data-driven services can be offered to a customer. Additionally, we have the collaboration interface, which is also connected to the IT platform. That means it can, let's say, have access to all the test data. And on this collaboration interface, our lab-to-field upscaling tools are implemented. And on the top, you can see the European Tribology Center. This will be the service provider for all these services which we have implemented in the project. As shown before, i-TRIBOMAT will offer 3 digital services. The service 1, the tribological testing of materials, the service 2, the tribological materials database, and the service 3, all the materials upscaling with simulation and modeling. Now we will show you a use case how to upscale materials via a seamless simulation workflow. We will show you the added value having right test data, for example of coefficient of friction, and how you can integrate this in a very seamless way into your simulation models. And this will speed up your simulation work, this will speed up your design of new products. And with this, I want to hand over to Donna.
Thank you, Franz. When we speak about digitalization, we mean the curation of data and its metadata descriptors, and also the capture of workflows for reporting and decision-making. This image is a reminder of some of the data that needs to be curated for the design, certification, and maintenance of dynamic components and systems, and that it comes from a variety of sources such as mechanical, tribology, surface experiments, virtual models and simulation, and so on. The reality is that for most manufacturing organizations, there is a huge challenge to bring all of the data and supporting evidence together. This is because it is scattered throughout the organization between multiple departments and filing cabinets and desktop PCs. And often, even if a report exists, there is a lot of knowledge that was not captured for aspects such as sample storage and handling, test environments, data handling, among many other examples that I'm sure you can think of as well. Speaking to the point of knowledge management, here are a few examples of points of pain related to tribology data for actors in a manufacturing organization as they face different requirements in their daily work. A lack of internationally accepted characterization standards has led to subjectivity in my results. I should investigate 2 different tribological systems and I cannot find coherent terminology used in these 2 applications. 2 test houses characterize the same part with different tribometers. I am not sure how to compare the results. Large numbers of specifically designed tribometers for niche applications make the consolidation of results difficult. I need to know the material properties and sample history of samples included in my tribological systems. All of these points of pain relate to different interpretations of tribology data. It is part of the remit of the project to harmonize these interpretations. The partners are using the ANSYS Granta MI database system. This is a commercially available materials information management system, and it is integrated in processes for scientists, engineers, and business decision makers. The system stores data for many different purposes according to a database schema. This database schema is tailored for application areas and is flexible to update. We'll look at some of the specific tables and records created with the support of project partners a bit later, but we just want to summarize here a few more capabilities of the system. The system is being used by partners to feed data and metadata to analytics, to validate protocols for modeling, and is integrated with several solvers, loading data from equipment and other databases, and to be able to automate workflows for different decision-making processes. Here we have a screenshot of the i-TRIBOMAT database frontend, powered by the ANSYS Granta MI system. And on the right-hand side, we have a brief example of some of the data and metadata captured by partners. Records in the database tables are linked such that we can find the samples used for a tribo test, along with its specific surface characterization and analysis methods with just a few clicks. And all of the information combined can be used to inform a simulation project. The database system is used by all project partners in a distributed way, thanks to cloud hosting, and it will also operate as part of the digital infrastructure of the future business, enabling aspects of capturing all the technical data as well as some key business information, hosting reference data sets, enabling interoperability between other IT infrastructures, and we will continue to work with partners to deliver on the envisioned digital solution. So let's now take a quick look at some of the data and metadata that's being curated for the project specifically for tribology. Here are a few screenshots that show a record with some of the terminology defined by the Partnership for Tribology Systems and an example of some of the raw data curves that are stored in the database ready for further analytics, such as modeling and simulation. So we are also working with expert partners such as BAM's Tribology representatives located in Berlin to curate some of their data sets and make them available to the new business and wider customer value chains of the partners. Here is an example of data available for early selection of tribological systems using our MI Explore interface. The systems of interest to your application may not be exactly the same, but such a data set can give you values for your early design decision making and point you in the right direction. At this point, I'm going to say thank you, and I'm going to pass on the presentation to our team member, Ulrike, who will walk us through a tribology case study.
So after my colleague Donna has now introduced you to the database structure of a TRIBOMAT, I will walk you through our use case. And for that use case, we chose the real application of a pneumatic actuator, which you can see on the right-hand side. And a new material group of interest are self-lubricating seals. So no external lubrication is required, and the seal is exposed to a reciprocating axial movement of the shaft, of course also to varying chamber pressures. We have a large system test rig in the consortium where you can measure different operating conditions, and the main interest is the efficiency of the system. So in the end you want to calculate and predict the frictional force and also the wear of the seal per cycle and the change of the wear volume till failure occurs, so the change in the profile of the seal. These are the results of interest that we also keep in mind to set up our simulation, which we will see in a couple of minutes. The use case seals is helping to set up all three services that i-TRIBOMAT is going to provide, which is service 1, combining all tribometers and analytical devices of the consortium in the so-called shared infrastructure. And on those tribometers, we are doing our model tests with the self-lubricating material. Then those results are transferred to the database, which you have already got to know. And then those data that are required as input for the simulation are transferred to service 3, which is essentially the upscaling simulation model that is going to predict the wear and friction and its lifetime for the specific material of interest. Here on the right hand side you see a seal compressed due to the chamber pressure acting on the red line, and you also see the surface where interaction between the seal material and the shaft on the left hand side is acting and where friction is occurring. I'm now going to show you the workflow that we use in the i-TRIBOMAT project. We essentially start with the industrial user's need and the new material of interest. Then via downscaling we go to the tribo testing and eventually to upscaling of the material behavior on the system level via simulation. So we start with the real application, and due to the wide potential range of applications of this compound group, we decided together with the customer that a system test rig available in the consortium is very well capable of performing typical operating conditions, and we have the advantage of all the measurement devices which are usually not equipped with an industrial pneumatic actuator. Basically, here we have a long stroke application over a couple of centimeters, and the chamber is filled with air. So with this information, we want to select a tribometer that is capable to represent the conditions the seal faces here in this system. And we call this process of selecting a tribometer from our shared infrastructure, we call this process downscaling. And in the use case of seal, we do this downscaling via simulation. That means we compress the seal in its housing using the real geometries of the profile and the housing. We apply the chamber pressure here on the red line, and then we extract the contact pressure that is building up here on this area between the shaft and the seal. And in the end, we want to have a tribometer that is capable of representing the range of contact pressures that we got out of the simulation here, together with typical velocities, strokes, temperatures, etc. And of course, for doing such a simulation, we need the right material constitutive law. And once we have that, we go to the Tribo testing and we want to perform a model test. Model test means we have a simple, easy to produce geometry of the material of interest, and we have a standardized test procedure how we deal with that. So when the material is changed, we can use the same procedure and do essentially the same type of test. So then the tribological conditions of are defined by the downscaling process, and the experimental output values we're most interested in are the friction as a time series, the temperature in the contact, and the wear rate. And with those, we go to the upscaling. So we use the output of the experimental test as input for the simulation in order to upscale to the system level. So we can simulate the geometries and the conditions on the system level, and we take the material specific behavior regarding tribology from the experimental tests. So let's have a closer look at those input and output values and the interface between the tribological experimental test and the simulation. So what are the input values that we are actually using to customize the simulation to the specific material application system? So first of all, that's of course the mechanical properties of the material, where we use tensile tests, compressive tests, biaxial tests. Yeah? The next is the surface topographies, where we measure the 3D topography illustrated here, and we use directly the 3D information for the simulation model. Next important input is the coefficient of friction that we derive from such a time series curve. And last but not least, the wear rate that we detect by weighing the samples gravimetrically after the test. So essentially, the lab to field upscaling model, lab is the model test, field is the system level, comprises of different models that you can combine flexibly and that you can customize flexibly to the specific case. So there is a material model. You can of course change the constitutive law there. There is a wear model, which is parameterized by the wear rate. There needs to be of course a kinematic model that captures the characteristic movement of the application of interest of the system. And there is a topography model which takes care of the disparity ratios, etc. And the output values are primarily the friction force at the shaft. We can resolve that along the movement in an outstroke and an instroke friction force, and compare that to a measurement and look at how this evolves for different operating conditions, different materials, and also if the geometry of the profile changes, which changes if we use the wear model. And then we are actually removing seal materials. So actually some of the elements are removed and no longer part of this seal. So we're not only detecting if and where is occurring, but we actually in the simulation change the profile of the seal, which then affects also the friction force. And we have collected all equations behind those models in a MODA, which is a system defined by the EMMC to set down the model equations and define the input value, the output values, and the processed output. So now we will have a closer look at all those input variables and how we obtain them. So thus we start with the constitutive material law. We are looking at the group of high-performance polyurethanes which are self-lubricating. Thus, they are meant to work without applying any additional lubricant. Therefore, we are also not lubricating any fluid flow between the polymer and the shaft surface. So only the polymer itself and the counterbody of the steel surface. So what do? We use tensile and compressive tests of each of those materials and fit a material model to it. We found out that a hyperelastic material model is most appropriate, and from the group of hyperelastic models, the third order yield model turned out to have the best fit in the region of interest. So here you can see the strain energy density function, and here the parameters we assigned as we assumed the material to be incompressible. All the other parameters are 0. So the next input value would be the coefficient of friction. The conventional approach is that you don't know the coefficient of friction between the counterbody and the specific material. You know qualitatively that the counterbody roughness is very critical, that the operating conditions can change it, but because you have no measured value, you're often forced as a simulation engineer to use educated guesses or go to some papers and use previous assumptions of another working group. So commonly values of around 0.2 are used, and this value is kept constant for all operating conditions and not changed for counterbody roughnesses, etc. Our solution is not to assume such a critical input value, but we want to measure it. And we can measure it in the tribological experiment. For that, we set up a model test which is standardized, which is done in the same way each time, well documented, and the output of this tribological experiment is well defined, and this is used as an input data for the simulation. And because we have it all in one hand, the simulation and the tribological experiment, and also how the data of the tribological experiment are processed in order to provide an input value for the simulation, we trust it, and we know exactly the quality, and we know that we're doing it the same way each time. So we offer a trusted data for the application for different materials. So in order to obtain this measured coefficient of friction, you have to first do a downscaling. So you go from the real application, you do a downscaling simulation, and then you can decide which model test configuration and parameters are appropriate. And with that information, you go to the shared infrastructure, to the database where all tribometers are collected, and you look for the appropriate tribometer. Then you perform all parameter variations of interest. You can vary contact pressure, sliding speed, sliding distance, and stroke. And the simulation determines what is needed and tells the experiment people which parameter variations are required. The output values are defined, whatever they change here in terms of parameters. So how does this test look like when we get our data? Here you see the instrument. It's one that is able to perform a linear reciprocative movement, and you can see that in this video. You can also see a thermocouple to measure the temperature in the pin, and the counterbody against which the pin is pressed has to reflect the counterbody in the real application exactly. This is what we checked here by measuring the 3D topography. You see it's a ground surface, and we're actually moving the pin perpendicular to the grounding grooves. So here you see some of the testing parameters, and again, we are not applying any lubricant. A typical time series of an output can look like that. So we record an average coefficient of friction. We also record the peak values of each cycle. And you see this is much higher and is exposed to a certain scatter. But both is recorded and both is stored in the database to be reused also later on for further benchmarks to other materials or other testing conditions. So from this time series, we extract the coefficient of friction in the steady state region, which is here. And for the conditions of interest, we found that a coefficient of friction of 0.6 applies to this material. And this is what we're going to use later on in the simulation. But we are also interested in wear, if potentially wear occurs in the time of interest. And for that we use the Archard wear law. So the wear coefficient, the Archard wear coefficient, which is proportional to the wear volume and linked to the normal load and the sliding distance, was found in the experiments to be between 3 and 5, 10 to the power of -9. And in order to speed up the simulation, we increased it to the power of -5. So that enables us to really simulate many cycles in a shorter simulation time. So these are examples for the real measured input data that we use for the simulation, and we will show on the next slides. So this is what the data look like in the database that was presented before. Basically, you have detailed entries of all different aspects of the test, like where and who has done it, on which tribometer it has been performed. You see the material, you see information on the counterbody, the topography can be shown, and you see the output values of the coefficient of friction. And you can even see the quality of the test via this hysteresis curve, which shows the coefficient of friction along the stroke of the back and forth movement. So this allows complete traceability. You can search for different criteria, and you can see the quality of the test and choose which values you actually want to use for your simulation. So as we have now all ingredients together for our simulation, I would now like to show you some of the results that we produced and illustrate the importance of the coefficient of friction on the contact area, also its influence on the friction force measured on the shaft, and on the wear volume, so how the profile changes. So let's look at the influence of the coefficient of friction on the contact area first. As you can see here on those cross sections for the 0 bar chamber pressure, when you increase the coefficient of friction, the contact area increases gradually. And at the end, the increase is rather steep. The same applies for another chamber pressure. Here, an example for 10 bar is shown. The contact area again increases just to other values. So whatever the operating conditions are, the qualitative information is the same. Higher coefficient of friction increases the contact area. And this higher contact area affects the macro shape massively, as you can see here. completely other parts are in contact with the shaft and can potentially provide sealing function. But this, on the negative side, will also affect the friction force, and it will get harder to move this shaft, which is negative for the efficiency of the system in the long run. Next, looking at the influence of coefficient of friction between polymer and steel shaft on the friction force measured on the shaft in the system. So, for instance, if we use a suggested coefficient of friction value of 0.2, which you frequently find if you have no experimental values, then for our system, for a 10 bar chamber pressure, we get 100 Newton as a friction force measured at the shaft. But if we use the experimentally determined value of 0.6, we get actually 400 Newtons. So you see, the friction force increases steeply with coefficient of friction, and this difference gets even higher with higher chamber pressure, so more severe operating conditions. So even for moderate operating conditions of 10 bars, a wrong coefficient of friction leads to a deviation of your prediction level of friction of 75%. So you increase a massive uncertainty in your prediction of your target value. So finally, let's look at the influence of this coefficient of friction on wear. If the coefficient of friction is higher, then this increases the friction energy in the contact area, and this directly affects the contact stresses, which also increase. And if contact stresses are higher, then the wear volume is higher, according to Archer's wear law as introduced before. And you see here in this graph that was produced with a constant Archer wear coefficient, that although for zero chamber pressure there is basically a baseline with constant wear volume, for higher chamber pressure this influence becomes highly pronounced, and the wear volume increases a lot if you increase the coefficient of friction. So now a more detailed look into the simulation results by looking at the stroke resolved results of the contact stresses during the in-stroke and the outstroke mode. We are in the in-stroke mode when the shaft is moving upwards, and we are in the outstroke mode when the shaft is moving downwards. You see the graphs of the contact stresses on the left-hand side for different coefficient of frictions. Let's first move to the outstroke mode at the bottom left picture. There you see, for all coefficient of frictions, the contact stress increases first to a maximum and then gradually decreases as you move on with the shaft. But this maximum increases pronouncedly as you increase the coefficient of friction, and thus also the decrease is smoother and takes a longer way until you reach zero contact stress. Qualitatively, the shape of the curve is the same in the in-stroke mode, so you increase the contact stress to a maximum and then you have a gradual decrease. But interestingly, the maximum is decreasing as you go to higher coefficient of friction values. However, this trend reverses as you move on. So at the coordinate of 1 millimeter, you see again higher contact stresses for higher coefficient of frictions. So the effect is more pronounced in the outstroke, but qualitatively for both modes, we have an increase of the contact stresses on the average level due to the coefficient of friction we extract from the experiment. And this leads to, in the end, higher wear and thus an increased danger of leakage. But note, we determine the wear and the coefficient of friction separately. They are not linked by a physical model. So whatever the test gives us, that's what we take here. So last but not least, I would like to show you a video of the simulation that shows the mounting procedure and then the wear due to the movement of the shaft. So you start here with the initial undeformed geometry of the seal. Then it's mounted into this housing, and then the movement of the shaft begins. So you see, you actually take away material, and this profile changes pronouncedly as wear increases. So you mount, and then the up and down movement starts. And we're not just detecting where wear occurs, we are actually taking away elements that take part in the simulation and carry load and stress strain information. As a conclusion, I would like to point out that we have achieved the standardization of tribological data that we measure experimentally of the surface, of the coefficient of friction, and the wear rate. So we have defined the file format, we have defined how we process the experimental data, and then we've integrated that in a seamless way into a workflow of the simulation. Which brings me to the third point. We think we really have a unique approach because we're not assuming any data. Every data that we use as input data are real data in the sense that we measured them and we know exactly the quality of the test and we know exactly how we processed the data. And this is so important because tribology describes a system property and you have to know all the metadata of the system in order to decide which data are your real data for the simulation that you're doing at the moment. And last but not least, the most important point is we have guaranteed a high flexibility in having separate models available. So you can choose to have a wear simulation. You can also easily turn it off. And you can choose flexibly between different materials. So after having summarized the simulation results, I would now like to summarize the i-TRIBOMAT services. One of the services is the simulation upscaling tool, which we have had a look at the case study of the seal, where we start from the model test with easy sample geometries that can be produced in large numbers and no special requirements. Then we upscale to the system level that contains the real geometry of the final component and the operating conditions of the system. The second service is the digital service for material data management. This is basically the database that has been presented before, which was generated by ANSYS Grantor within the i-TRIBOMAT project and ensures traceability and reusability of the data for future benchmark and future use in simulations to come. And the third service is the large variety of the shared infrastructure of tribometers along with the characterization methods supported by more than 250 experts. And we do not only want you to know that there are those three services, but we would actually love if you test those services and if you become one of our early adopters. So please note there is an open call for early adopters that will be launched in December this year. So stay tuned. Please go to our website and get in contact to us if you're curious, if you just want to test us. And yeah, if you want to become early adopters, please feel free. We would be very happy to meet you.
Thank you, Donna, and thank you, Ulrike, for the technical presentation. But I want also say thank you to all our colleagues and all our partners in this project. Many, many thanks. And now you're welcome to ask questions, and we will be happy to answer them.